Today's the 19th, isn't it? Okay, so we have f of x equals natural log.
Tangent squared. Times the tangent squared.
Natural log of what?
Times the tangent squared.
Oh, of tangent squared of x. Is that correct?
Yes.
So it's natural log applied to tangent squared. Okay, excellent. And what we want to determine here?
Discontinuity.
Okay, so find where this function is discontinuous. That's it? Nothing else. Is there any information, other information given? No. Okay. Find discontinuities. Okay, excellent. So first, we will be looking at this function for a moment. So natural log, I know that the inside, the argument, in other words, of natural log must be what type of number? And never zero, correct. You are absolutely correct. So it has to be positive, but I just want to super specify it cannot be zero, which is very clear. Jet said positive, so obviously it's not zero. But I just want to make sure that it's very clear also, not zero. Good. Now I look inside. And inside I see tangent squared. Okay. Tangent squared is positive, but it could be zero. Okay. So the first condition that I have to look at is tangent squared not to be zero, because this quantity has to be strictly greater than zero. That's the first condition that I have to consider. Would you agree so far? Okay. However, there is a second condition. Why? Why is there a second condition? The second condition comes from the fact that this 4 tangent is not a nice function. It could be undefined. It's a function with vertical asymptotes. It's not a nice function. It could be undefined when its denominator, which is cosine, could be zero. So the second condition is that cosine does not equal zero. Okay, so it's a very interesting problem. Are we restricted to a particular interval or anything? It just says everything?
Yeah, basically.
Okay. So, first of all, I look at natural log, and I know that the quantity inside natural log has to be a positive number. I'm happy. When I see tangent squared, I'm very happy. But there is a problem, because tangent squared could be zero, number one. Number two, I look inside and I see tangent, and I say, oh no. Tangent could be undefined because it's a ratio of sine over cosine. So I cannot have here something that is undefined, and I cannot have in here something that is zero. Does it make sense? Okay, so we have to analyze these two conditions now and see where it takes us. Very interesting problem. Tangent squared not zero is the same with tangent not zero. Where is tangent zero? So I'm talking about the first condition first. So tangent x is sine x over cosine x. When is a fraction zero? Only when the numerator is zero, correct? So let's see, when is sine zero? Millions of places. Remember, sine is measured on the y-axis. So on a complete circle, just give me on the complete circle for now. X, sine x is zero means that x equals 0 plus 2 pi k, actually, with k 1, I'm sorry, 0 plus or minus 1 plus or minus 2 and so on and so forth. So it can be this point. We can condense them. And the other point is plus 2 pi k. But these two really are together in pi plus 2 pi k. Or let me see if I can get the 0. 0 plus 2 pi k. So I will put 0 plus pi k. So in order to condense these two, I could write, in order to have both of them in one line, I would write pi k. Let's check. Let's check if we get with this solution, if I get all of these. When k is 0, I get this. When k is 1, I get this. When k is 2, I get this. When k is 3, I get this. When k is negative 1, I get this. When k is negative 2, I get this. When k is negative 3, I get this. So this is the condensed both. Do you have to condense it? No, but I don't know how they want the answer. That's my problem. So these are fine. Or this. For both of them. This or these are fine. You don't have to condense it. Okay, so this is just number 1. So where will for sure, for now, just for number 1, where for sure will this function have discontinuities? It will have discontinuities at any pi k where k is a rational number. Is this it? No. Now I have to worry about the second possibility where this is undefined. And if this is undefined, natural log of undefined is undefined. It doesn't exist. So now I have to take care of this. So in number 2, I have to solve the equation cosine x equals 0. Well, when I solve the equation cosine x equals 0, I get these. That's where cosine is 0. So I will get x equals pi over 2 plus 2 pi k, and x equals 3 pi over 2 plus 2 pi k. Pi over 2 plus 2 pi k, and 3 pi over 2 plus 2 pi k. I'm going to try to condense these two to see what happens, because I have to put these two together now with the pi k. Turns out to be quite interesting. So the solutions for this would be pi over 2 plus pi k. Let's see if we get all the solutions. When k is 0, I get this. When k is 1, I get this plus pi. When k is 2, I get this plus and back here. Yes. So this is the condensed of this. And now I have to put these two together. Do they say write the answer with a comma, or we can condense these two now? Again, how do we condense? So basically, our discontinuities are here, 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 here. These are all discontinuities. So let's see if we can write pi over 2k. Let's see if this gives all those 4 different solutions. Let's check. When k is 0, I get this. When k is 1, I get this. When k is 2, I get this. When k is 3, I get this. When k is 4, I get this. Do they explain in the question that you will have to use a k, which is an integer, anything from 0 plus or minus 1 plus or minus 2?
Steve N.
Say it again.
Steve N.
So looking for discontinuity, use n where appropriate infinite discontinuity. So in that case, they want k, n instead of k. So then x will be pi over 2n. It is true, some books use n instead of k, others use k. It doesn't matter. It's the same thing. Is this okay? Yes? Better?
Yes.
Feel better about it? It was quite an interesting problem. Thank you so much for bringing it to class. Excellent. Good. Anything else? Anything else? Anything else? Okay, in that case, do we have anything left, any leftovers from the previous section, or what I would like, if possible, because our class is 13-week class, I would like us to maybe finish 2.7 and 2.8 in 1 hour and then start reviewing already. And then on Monday, just use maybe, unless you have questions, I have to answer your questions, maybe use just 1 hour to review and then continue chapter 3, which will not be on this test, of course. Let's see how it goes, okay? We'll decide as we go along. Okay. Do we have any leftover from the previous sections? Any questions? I think we looked at a lot of problems. Oh, since we are here, I'd like to look at a problem from this previous test. See if we do this problem or any other, it's the same thing. Okay, so this will basically wrap up section 2.6. Okay, here I see a function, which is a rational function. I'm going to copy it. This is problem 8 on page 8, in which we have f of x equals x plus 1 divided by x squared plus 3x plus 2. And the problem is asking us to find all asymptotes and, of course, the corresponding limits. Why we are also asked to find the corresponding limits, you will see in chapter 4. Okay, so please bear with me. Okay, so in this problem, the first thing I'm going to do is, what do you think? Oh, of course, thank you very much. I will factor the denominator. How do we factor the denominator? Very good. I know you are tempted to simplify the x plus 1 with x plus 1. I would too, but not before we write the domain or the restrictions. We will simplify, but not before I write two restrictions. If I do not write them now, then I will not be able to write them after I simplify because the factor will disappear. And that would be a terrible mistake. Okay, so then I know this function is not defined at -2 and -1. After that, indeed, I will simplify fully and write that this function simplifies to x plus 2, but the restrictions stay because they stay and they are stated on the function, not on the simplified form. Now, there are two situations here that I'm sure you discussed in pre-calc, but I will have to discuss them again today. If the factor of x plus 1 disappeared, at x equals -1, the function has a hole. The final still has the x plus 2 in the denominator, which makes x equals -2 a vertical asymptote. Please understand the difference. The factor that stays creates the vertical asymptote. The factor that disappears creates a hole. If x minus x plus 1 does not go away with the factor from the top, then we have two vertical asymptotes. But because x plus 1 cancels with the factor of x plus 1 from the numerator, the restriction still stays. but the function will have a hole at that point. Okay, how do we show that? Here's how we show it. So number one, limit as x approaches -1 from the left of the simplified function, simplified form, and limit as x approaches -1 from the right of 1 over x plus 2. Then, after we finish this, we will determine the limit as x approaches -2 from the left of 1 over x plus 2, and limit as x approaches -2 from the right of 1 over x plus 2. These are completely separate. They're not together. So can anyone give us the limit on the left? This limit, I meant, and this limit. This one is, and this one is. If it's a whole, it must be the same.
Yeah, right.
Good. So what, can anyone give us the ordered pair that is the whole? Excellent. Thank you. That is the whole. The function values get closer and closer to 1, but the function is undefined at that point. And we know that that's possible. The function has a limit there, although it's undefined there. We know that has nothing to do with anything, right? A function can have a limit at a point where it's undefined. What type of discontinuity is this? Excellent. It's a removable discontinuity because the limit from the left equals the limit from the right, but not equal the function value at that point. So this is a removable discontinuity. I can create a function that is continuous. But this discontinuity, I cannot. The jump discontinuity, I cannot. But the removable, I can. Okay, perfect. Can anyone give us the limits here? Yes, -2.1, very good, and very good. So this is positive infinity. Therefore, for this reason or these reasons, we have x equals -2 of VA. That part is done. So we identified the vertical asymptotes and the whole. Now, the second step is I want to determine the limit as x approaches infinity from 1 over x plus 2, the simplified form, and also when x approaches -infinity. But it's a rational function. I don't have to separate those. They will be the same answer. For rational functions, there is only one horizontal asymptote. I can't have one on one side and a different one on the other. So the answer is excellent, which means y equals 0, horizontal asymptote. Done. So when we are given a function and we are asked to find where it's undefined or where it has vertical asymptotes or horizontal asymptotes, we have to determine the corresponding limits. So it's not sufficient to say, oh, there is a vertical asymptote at -2. Oh, there is a hole at -1. No, we have to show the limits, like we did here. So that was another type of problem that I wanted to show you. And we already looked at this one. I don't see anything else. I think we covered everything in this section that we need. So I would like to move on.
So you determined that was 0 because it was...
When x approaches infinity, I have, let's say, a piece of a cake, and I want to divvy up into infinite people. When I get to you, how much will you get for my cake? Nothing. Especially if I start in China and India. Very soon I'm not going to get anything. Okay, for anyone. So 1 over infinity is approaching 0 or equals 0. Okay, 2.7 and 2.8. I don't want to put the title just yet. We're going to come back and put the title in. So we looked at two concepts so far. Two major concepts from the very beginning of the semester. One of them was the difference quotient. So number one was the difference quotient, which is f of x plus h. We have to memorize this, minus f of x divided by h. What does this give? The average rate of change between 2 points. But remember, these 2 points are very, very close to each other. Can I say that this does not equal to, but this is approximately the slope of the tangent line? I still know how to write tangent at P. Can I say it's approximately because x and x plus h are very close, not the same point, but they're very close to each other. Can I say that this is almost, not exactly, the slope of the tangent line at P? Could I? Okay. The second concept that we worked on, and we haven't really learned anything else. I hate to disappoint you, but everything else was just a little tangent here and a little tangent here from these two concepts. What was the second concept that we looked at? Of course, the limit operator. That's it. So I want now to determine the slope of the tangent line exactly. Slope of the tangent at P at any point. There is something missing here that I will explain in a moment, to be exact. I want to put these two concepts together to get to the tangent, the slope of the tangent line. And how do I put these two concepts together? I put the limit in front of it. As h approaches 0. Once I put the limit, as h approaches 0, of the difference quotient, I determine the slope of the tangent line at any point. And this is nothing else but what we call f prime of x. The name is the derivative function of f of x. I'm coming back to this gap here. The gap is very important. 1 second. So in a month, roughly, we learned to calculate and determine and simplify the difference quotient for different functions. And then we learned how to use the limit operator. Now we're putting these two together. The limit of the difference quotient is the derivative. But what does this mean? Here's what it means. The derivative of this function gives, it's a function. F prime of x is a function, is the derivative of this function f of x, gives the slope of the tangent line at any point, and now I'm triggering this gap, where f of x is, I have never used this word before in this class, differentiable. And now we have to talk about this. So, I'm really telling you that we have functions that do not have a tangent at certain points. That's what I'm telling you. They don't have one. They do not have one tangent at certain points, which means at those points the function is not differentiable. It doesn't have a derivative. In how many ways can that happen? Here are the ways. This is one. Here's another. Here's another. And here's one more. Last one, I promise. Let's start from here. Is this function continuous? Yeah, this is an absolute value function, right? Shifted a little bit. Yes, this is a continuous function. But look what happens at this point, which is called a corner. At this point, the function has a tangent here, which is positive, and a tangent here, which is negative. It does not have one tangent, a unique tangent. So when a function is continuous and has a corner, at this particular corner, it does not have a derivative because it doesn't have just one tangent. Okay, this is called a cusp, like between two teeth. Same idea. This is one tangent that is positive, and this is a different tangent that is negative. So at that point, at that cusp, this function is not differentiable. Although, is it continuous?
Yes,
It's continuous, but it's not differentiable at that point because it doesn't have just one tangent. So, for example, here, the function is differentiable because it has only one tangent. Here, it's not continuous and it has a positive tangent, I don't know, maybe 1/2, but it also has another tangent here with a different slope. Even if the slopes were the same, I couldn't care less. It's not just one tangent. This line is this line, which has nothing to do with this line. So this is discontinuous. If it's discontinuous, it cannot be differentiable. Last example. Is this last example continuous? The answer is yes. It's continuous. But look what happens at this point. The tangent is what is the slope of a vertical line? Undefined. Undefined. So if a function is continuous and has a cusp corner or it has a vertical tangent, these are not differentiable. These functions are not differentiable at those points. There is no discussion if the function is not continuous, it cannot be differentiable. So, question, if a function is continuous, can I draw the conclusion that it's differentiable? No. Question, if a function is differentiable, does it have to be continuous?
No. Yes.
Absolutely continuous. So please write this down. Continuity does not imply differentiability. But differentiability absolutely implies continuity. If a function is continuous, you may have a cusp, corner, or vertical tangent. It's not going to be differentiable. But if I tell you that the function is differentiable, it must be continuous, otherwise it will not be differentiable. Okay. There is only one formal definition of the derivative. I'm going to write it one more time. We already know it. So derivative function has only one definition. F prime of x equals the limit as h approaches 0 from f of x plus h minus f of x divided by h. This is the derivative function. I would like to choose one function that is extremely important and determine its derivative using the definition. Okay, so the function, I know it's your first love. We discussed it. This must be it. And the second love, not just the first. Brian just gave me a nice look. Okay, so what is she talking about? Okay, so we are all in love with the square root of x for the next 10 minutes, 5 minutes. Okay, we want to find f prime of x. And when we find f prime of x, moving forward, we will never ever find it with a definition, and we will never forget it. Agreed? Excellent. Good. So please dictate the definition. Please tell me what to write. I'm ready. Excellent. Now we know not all techniques of finding limits, but we know enough to come up with an idea for this one. So can you come up with an idea for me?
Multiply by time.
Right, because this is 0 over 0. So the first thing we do when we calculate limits, we plug it in just for safety. Because if the answer is 5/3, then I'm done. I don't have to rationalize anything. But in this case, of course, it's 0 over 0 is expected. Two things have to happen. What are those two things that have to happen? Whenever I calculate the difference quotient, blah, blah, blah. No, yes, that's the second one. And no terms without age. Yes, all of them go away. Good. So now we're ready to multiply. I'm going to change this for laziness into the square root of x plus age plus the square root of x, the square root of x plus age plus the square root of x. And let's see what happens next. I lost track of my numbers. So one other thing that I want to make sure that this is clear to all of you. The derivative is what exactly? A what? A limit. A limit. And this answer cannot be infinity. That's why the function having a vertical tangent has a limit that is infinity. The derivative is infinity. I can't have a limit. It does not exist, right? Okay, so can anyone tell us the next step? Limit as age approaches 0 from? Perfect. These two go away. And don't forget the age, like I did. I said, oops, something is wrong. Where is my age? Okay. Good. Of course, now I simplify age from the top with this age in the denominator. And that's the second thing that has to happen. All terms without age go away from the top, and now that's this age. And now I can finally drop the limit operator. The answer must be a function. And what is the function? That's why I'm allowed to drop the limit operator, because I have to make that this approaches 0. So moving forward, we proved that f prime of x is 1 over 2 the square root of x, and this will be carved in stone moving forward. We proved it with a definition. So the square root of x prime is, maybe I shouldn't write it like this because it's not clear. I should write it like this. But you know what I mean. I was talking about the previous function, but I think this is better. Moving forward, the derivative of the square root of x is 1 over 2 the square root of x. And I want to talk about this for one more second. I'm going to graph it. I'm going to graph the square root of x. Ready? Let me know if you agree with my graph. Agreed? What do you see here? If you want, or a vertical tangent, right? Yes. Okay, I claim that x is continuous on 0 to infinity, but I claim it's not differentiable at x equals 0. And you can say, really? Yes. Can you tell me whether this function exists at x equals 0? No. So therefore, the function itself is not differentiable at 0. This is defined on greater than or equal to 0. This is defined on x greater than 0. Why? Because at this point, it has a vertical tangent. It cannot be, the derivative does not exist there. We say the function is not differentiable at 0 because it doesn't have a derivative. Why doesn't have a derivative? Because the derivative at 0, the derivative at 0 will be infinity. The limit will be infinity. Will not be a number. A derivative is a limit. Okay, so that was one example. Moving forward, please, this has to be carved in stone. And now, let's take a look at two situations side by side. I'm just changing the notation on you. It's really nothing. And you'll see why in a minute, why we change the notation. What is this height? If this is A, what is this? Okay. This is X. What is this? F prime of A will be the slope of the tangent line at A comma f of A, at P. Slope of tangent at P. Can anyone give us the definition? So this is f prime of A. It will give us only the slope of the tangent line at P. So please tell me how to write it. How do I start? How do I start? Thank you. S thank you. From oh this is one definition of f prime of x. Of course, on this side we'll have one more. So one definition for f prime of x, but you will see two definitions for f prime of A. So this is a number. This one, a function. f prime of x, a function. This one, a number, whatever. If the function is differentiable there, of course. If this is infinity, then the function is not differentiable at a, or at p if you want. So this is one definition. We have one more. And you can say, really? We really need one more? No, it's the same thing, basically. You'll see in a moment. This is still a. This is still f of a. This is still q, but now this is a plus h. It's the same thing, but replaced x by a. So this is f of a plus h. So can anyone give us a second definition of the slope of the tangent line at p? We just used x instead of, yes. No. You mean before here? Yes. Yes. So here we have a in this case. A. Still age approaches 0, still age in the denominator. So this the second option would be limit. Still was as f of a plus h minus f of a divided by h. So everything is exactly the same. Now, if you ask me, okay, you're giving me a function, you're asking me to find f prime, should I use this definition or should I use this definition? Well, for some functions, this one would be easier. For other functions, this one would be easier to calculate, but it doesn't matter. The calculation may take longer, but you're going to get the same answer no matter what. Okay, so now I'm ready to go over some examples. So for f prime of a, choose anything you like, 27 through 32. And then here, on page 163, from 21 to 31, let's work on any problem. I really like the graphs. They're identical graphs. I really like the graphs on page 159. As you see, this is not differentiable because it's not continuous. They do not present the cusp. They say that this is a corner. You can consider it a corner if that's what you want. That's fine, but this is a cusp. And this is a vertical tangent. And I like specifically this when they show the existence of multiple tangents or two tangents here. So they say, okay, maybe that is considered even a vertical. That's fine too. I'm fine. But there is no, you either say it's a, in this case, a vertical tangent, or you say it has two tangents left and right. Pretty similar. I kind of, in a way, disagree with this a little bit, but you got the idea. That's pretty much what we needed. It's either a vertical tangent or more than one tangent at a point. So still. Okay, so would you like to choose, and would you like to determine the derivative of any function? So basically, they consider the cusp as having a vertical tangent, and they consider the corner as having two tangents. That's fine. Okay, so would you like to start with f prime of x or with f prime of a?
23.
This one? Okay, very good. So let's start with 23. So that is 23 on page 163. And that is f of t equals 5t minus 9t squared. Since the variable is t, of course, we are asked to find f prime of t. Can anyone give us a definition? What do I have to write?
5t plus limit of
There is only one definition for this, right? So the definition for the function is always just limit as age approaches 0 from the difference quotient. If I'm asked to find f prime of 2, then I have two options. But if I'm asked to find f prime of t, I only have one option. Yeah. So then you can write it as f of t plus age minus f of t first so you don't get confused. So this is the difference quotient. The only difference is now that the function has t in it but not x. But that's okay. And now tell me what do we write next. Limit as age approaches 0. Yes, 5t plus age in parentheses minus 9t plus age squared minus 5t but plus 9t squared and over h. Regardless of what this is, f prime of 2 or f prime of t, we know two things have to happen. I know I sound like a broken record, but this is what we have to have in the back of our minds. Otherwise, I know I have an error and I have to go back from scratch. So two things have to happen, right? Terms without h from the top have to go away, and eventually this little h has to go away. Clear? Okay, perfect. So at any point in time, you can tell me, we got it. You don't have to say it again. And I'll keep my mouth shut. I can never keep my mouth shut, though. But for you, I will. Okay, so we have 5t plus 5h minus 9. Careful with this, because this is t squared plus 2th and plus h squared minus 5t and plus 9t squared divided by h. So remember, we have to square first, and when we square binomial, what do we get? Perfect. So I can already get rid of these two, so I don't have to write them again. So this is limit as h approaches 0, 5h minus 9t squared minus 18th minus 9h squared and plus 9t squared over h. And by plan, as expected, everything without h is gone. Now, again as expected, I pull out an h. I get 5 minus 18t minus 9h divided by h. That's how that guy from the denominator disappears. And now, only now, I can drop the limit operator. And the answer is?
Can you explain?
Yes?
You do that a couple times. What's the thought process behind when you can remove the limit operator?
I remove the limit operator when I replace h by 0. Never before. Now I can remove the limit operator and write negative 18t plus 5.
In the case because we're plugging in 0, that's why you're saying you get the 9.
Exactly. So at the final stage, when I replace h by 0, the limit operator goes away. So I know this looks much more different than this, but there is no difference. Here it is in the concept. The square root of 9, I apply the square root to 9 and I get 3. And that's exactly what I'm doing. I'm applying limit as h approaches 0 to this function. I applied it. That's how I get negative 18t plus 5. Versus the square root of 9 equals the square root of 3. That makes no sense. I already applied the square root to 9. I cannot keep it. So that's why there is no reason to still keep the limit operator. I applied the limit to it. So this is Not necessary. That would be wrong. Not. So when h approaches 0, this goes away. So the answer is negative 18t plus 5. Any questions? So with the same thing, let's look at f prime of a, but this time let's choose a different function. (27 to 32). Let's use a different function for this. A rational function is extremely important, although we have looked in the past at many of those. But I think it's useful. Maybe this one, which is x to negative 2. It's up to you. You choose.
Irrational.
Rational, very good. So you want this one, 29? Okay.